Guys, welcome back to Curious Minds. In this video, I'll be talking about what is a pulsar, what is a quasar, and the history behind them. Now, for the video. In 1960s, the discovery of two new phenomena, pulsars and quasars, sparked astrophysical research that continues to yield important results. Both are powered by collapsed ultra-dense objects that share some properties by virtue of their extreme nature. However, they are different phenomena. Pulsars are associated with endpoint of the life cycle of some stars, while quasars are associated with galactic centers. Now, pulsars are rotating neutron stars, dense stellar cores left after a star implodes and then explodes during a catastrophic event known as a supernova. Their existence was predicted in 1932, the year when neutron was discovered. When the Russian physicist Lev Landau wondered if stars could contain neutronic matter deep within their cores. At the time, no one knew how to detect a neutron star. They were later discovered in the experiment designed to detect radio galaxies, which were ultimately linked with quasars. Quasars are energetic powerhouses of nuclei in their galaxies. Most luminous objects in the sky device in the universe, and the discovery came as a complete surprise. Though both were discovered by analyzing low energy radio waves, they have been studied with higher energy X rays and gamma rays, giving astronomers a glimpse of violent phenomena in the universe. Recently, pulsars have allowed observation tests of general relativity, and quasars are being used to map the distribution of matter filaments at the larger scale of the cosmic structure. Now, the historical background, and scientific foundations. Now, the discovery of pulsars. In 1967, Anthony Hewish and his graduate student Jones Lee Bell built an array of radio at Antony to survive over 1,000 radio galaxies. Unlike optical telescope, which collect and focus the light in visible wavelengths, radio telescopes tune in long wavelength electromagnetic waves. Because Hewish was interested in rapid variations in the intensity of the sources and data from array recorded by movable pens on scrolling charts, one day the observation produced almost 100 feet, which is 30 meters of paper at the time. Any form of digital recording would have been probably expensive. A few weeks after beginning the survey, Bell noticed a bit of scurf on the charts that didn't look like any other radio galaxy or local noise. The source appeared as a pulse that repeatedly, precisely every 1.3373011 seconds. Further, each pulse lasted only 0.016 seconds, indicating that the source was compact. The distance was found to be 214 light years beyond the distance of nearest stars, but typically stellar distance. After carrying out enough observations to rule out significant from extraterrestrial civilizations, a time that Hewish later described the most exciting in his life, he proposed that the source could be a white dwarf or a neutron star undergoing periodic oscillation. These new objects were dubbed as pulsars for pulsing radio sources. Now, the early theoretical work on neutron stars. Much of the theory of white dwarf stars were developed in 1920s by Indian American born astrophysicist Subhaya Chandrasekhar, who applied the concept of quantum mechanics in the interior of the stars. Once a star exhausts its nuclear fuel, he reasoned it would contact under the gravity until the Pauli exhaustion principle that caused electrons to exert a repulsive force. This force could support stars up to a maximum mass about 1.4 times than the sun's mass. For higher masses, a white dwarf could collapse to even a denser object. The theoreticians were also exploring the endpoints of stellar life cycles around this time. In 1934, astronomers Walter Beatty and Fritz Zwicky predicted that the explosion of massive star in a supernova would leave behind a remnant even denser than the white dwarf, a cluster of closely packed neutrons that they dubbed as a neutron star. In 1939, J. Robert Oppenheimer and George Volkoff published a detailed theoretical model indicating that neutron stars would have a great mass than the suns with probably radius of only 6.2 miles, which is 10 meters. This is a tiny size implied two things. Neutron stars. The first is that neutron stars would have extremely high densities, approximately 10 power 14 gram centimeter square gram centimeter cube, far greater than the sun's average density of 1.4 gram centimeter cube and roughly equivalent to that of a neutron itself. And the second thing would be difficult to detect. Yes, it would be difficult to detect. Now, how do they connected neutrons and pulsars? After Hewish Bell, three collaborators announced their pulsar discovery in February 1968. Pulsars quickly became a popular research item during the remaining 10 months of the year. More than 100 papers detailing new observations of pulsars or attempts to decipher the pulsar phenomena was published. The correction interpretation was given by Franco Pansini, an Italian astrophysicist who was visiting Cornell a few months before Hewish and Bell made their discovery. Pansini predicted that the rapidly rotating neutron stars with strong magnetic fields could accelerate electrons to the point and they emitted large amounts of beamed energy, the radio energy that Hewish and Bell detected. Two beams would shoot out their stars in opposite directions and one from each other magnetic pole as the star rotated. One of these beams might happen to sweep repeatedly over our own location, producing a pulsating signal like blink of rotating or lighthouse light. Fancy's model was known as Lighthouse Model that predicted sources that were ultra compact by astronomical standards, otherwise, the rapid rotation would tear the object apart. In 1968, a year after Passini's work, Thomas Gould, another Cornell astronomer, independently proposed rotating neutron stars are source of pulsar radiation. Ironically, Gould's and Passini's officers were almost side by side. Only after their papers were published did the two scientists realize that they had a common theoretical interest. They published a joint paper a month later. Further discoveries that year helped pull their entire picture together. Pulsars were observed in Crab and Vela nebulae, two clouds of gas known as remnants of supernova, verifying Baird and Stiglitz 1934 theory. The Vela pulsar had a period of 89 milliseconds and Crab pulsar was even shorter, only 33 milliseconds, implying that these objects were spinning at an outstanding 11 to 30 times per second, respectively. In comparison, the sun spins around once in a month, Earth once in a day. Only neutron stars could spin that fast without being disrupted. Passini and Gould had each other predicted that pulsars could slow down over time, and the verification of this slight effect in Crab pulsar removed any illogical doubts about the pulsars were rotating neutron stars. Enormous densities of neutron stars help them keep extraordinarily accurate time. The Crab pulsar is slowing 36.5 nanoseconds per day. At this rate, it would take more than 75,000 years to lose a single second. However, a handful of pulsars and their periods disrupted for several weeks in distribution of glitch before settling back into their old pattern or spin down. These are being studied to learn about neutron stars in bizarre interiors as some geographical study vibration from earthquakes to near inner core structure. So that's all about pulsars and quasars. Hope you like this video. If you hit the like button and if you want more videos, don't forget to subscribe to Curious Minds. Having any ideas or topics which you want me to speak, suggest in the comment box. Until a good video, this is me, Curious Minds, signing off. Bye.